All right, hello everyone. So we are back with another lecture. Today we are going to continue binary search. We are going to look at some questions that have been asked in companies, in some of the top companies, right, regarding binary search. Now, as always, after the lecture is over, we would recommend that you find a link in the video description. That link gives you the problem set. Right? So after every class, you are supposed to do a problem set so that you can actually practice whatever you have learned in the class. Right? So you'll find that link in the video description. Now, without further ado, let us start the class. So let me just share my screen. All right. I hope that everyone can see the screen and whatever I'm writing over here. Cool. So let us start with a question directly. So yesterday we had looked at what binary search was and how to implement binary search. Let us dive into one question today. Okay. So suppose that you have been given an array, right? And this array has n integers. All right. Now it has also been told to you that in this array, all elements but one come twice. Come twice. All right. Also, it has been said that the array is sorted. Array is sorted. So let us first take an example of such an array. Let's look at such an example. Let's say that we have 0, 0. We have 4, 4 minus. We have, let's say, 5. All right. We have 5 over here, suppose. Right? Then we have, let's say, something like 7, 7, and we have 8, 8. Right. So in this array, we see that every element has been repeated twice. There are 2 zeros, there are 2 4s, there are 2 7s, there are 2 8s, except for one element. Right? Except for one element, every element is repeated twice. Also, this array is sorted. Right? So it is sorted in ascending order. Can you guys not hear me? I hope my voice is clear. All right. Cool. Now the question says you have to find this singlet element. Right? You have to find this element which occurs only one time. So if this was the array that was given to you as input, then you are supposed to return 5. Is the question clear? Yes. So we have been given an array. It is sorted. Every element in the array occurs twice, except for one element. And we have to find that one element that occurs only once. All right. So let us see some approaches. Let us see some approaches. So Piyush has a very nice idea over here. Piyush says, let's try XOR. Right now, we all know the property of XOR. We have seen that in the bit manipulation class. That XOR acts like a lock and key. Lock and key. Right? Basically, if I XOR the entire array, that is supposed to give me that element that occurs only once. Right? That element. I'm supposed to get the correct answer because all these things will cancel, right? 0 XOR 0 will cancel, 4 XOR 4 will cancel, 7 XOR 7 will cancel, 8 XOR 8 will cancel, and I will be left with 5. So yes, that's a valid approach. That is totally a valid approach. What is the time complexity of this? How much time will this take? How much time will this take? This will take order of n time, right? Because we have to go over each element and check. Right? We have to XOR each element. All right. Cool enough. Can we do better? In this, using this XOR thing, are we first of all making use of this property? We know that the array is sorted, right? We know that the array is sorted. So either if we use XOR or if we use a map to keep a count, then we are not really using this sorted property, right? We are going over each element. So let us try to make use of this sorted property and see if we can reduce the time complexity. So this is a valid brute force approach. But let us come up with an optimized solution that exploits the property that the array is sorted. Yes, let us see if we have some other approaches. All right. So yes, binary search would be the answer here. But what exactly are you going to do with the binary search? How exactly are you going to search it? All right. So Anurag over here says that let us check the middle element. Let us check the middle element. All right. Let us suppose we have some middle element. And what Anurag is saying is let us compare it with the previous or next element. Right. And then return. Well, let us suppose that this array was a little longer. Right. Let us say that we had 10 over here as well. Right. So when you find the middle element, let me just add the indices. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. So what will be the middle element? This will be the middle element. Right. Cool. Now, if this is the middle element, then we compare it with the left and right element, and what exactly do we do? What exactly do we do? So we look at both neighbors. We look at both the neighbors. All right. This is 5 and this is 7. So how does that help us? How does that help us? It doesn't really help us, right? Okay. So what can we do then? Yes. So Dipanshu has a nice idea over here. Let me just show Dipanshu's comment. So Dipanshu says that let us observe one thing. Let us observe one thing. That whenever a new element comes, it always comes at an even position. Right? Whenever a new element comes, it always comes at an even position. Yes? Is that correct? Until and unless that middle element comes. After that, every new element comes at an odd position. Do you all agree? Yes, the first occurrence of any element is on an even position on the left side of this mid and is on an odd position on the right side of this mid. Do you guys observe that? So we are going to use this property. We are going to use this observation to find out what the single occurrence element is. Right? So suppose that we do something like this. We pick, so we have a high and we have a low. Right? So this is 5 and this is 8. We have a low and we have a high. Right? Let us calculate some mid. Right? Let us calculate some mid. What we will do is this mid will be, let us say, A of mid. Right? This A of mid, it might be the first occurrence of this value or it might be the second occurrence of this value. Right? We don't really know. This 7 that we landed on, this could be the first occurrence of 7 or this could be the last occurrence of 7. Right? We don't really know. So what we can do is we can find the first occurrence of 7. Suppose that we landed on this bit. Suppose that we had landed on this bit. Then we can compare it with the previous element and always find the first occurrence. First occurrence of A of mid. Can we do that? Yes. Given a mid number, can we find A of mid and then can we find the first occurrence of A of mid? It will either be that element itself or it will be just the previous element. Right? Cool. Now, once we have that, we can check if the index of first occurrence of A of mid, right? If this is even, then what does that mean? What does that mean? That the singlet element lies to the right of me. Right? Whenever I find the first occurrence at an even position, that means that a singlet element lies to the right of me. So I will move right in this case. Right? On the other hand, if this is not the case, if it is odd, then I will move left. Yes? And I will also have to stop at some point. Right? I will also have to stop at some point. So I can check. If A of mid is the first occurrence, and there's only one occurrence, right? So A of mid plus 1 is not equal to A of mid, then I know that I have found my singlet element because it occurs only once. Does that make sense? Yes. So what will be the very quick pseudocode for this? So we will start with low equals to 0. We will start with high equals to length of, so AR dot length minus 1, right? Then we will loop while low is less than equal to high, right? What will we do? So we will calculate the mid first. So we will say mid equals to low plus high minus low by 2. Yes, we just calculated the mid. Remove the extra string comment, surely. Yes, cool. All right, so we calculate the mid, then we can check. So we will first check. So we know that we have to find the first occurrence of A of mid. Right? How do we find the first occurrence of A of mid? Well, we can check over here. We can check if A of mid minus 1 equals to A of mid. Right? If this is the case, then A of mid is the second occurrence and not the first occurrence. Do you agree? Yes, if A of mid minus 1 is equal to A of mid, then A of mid must be the second occurrence because the previous element is also equal to it. In this case, what is the first occurrence? The first occurrence is mid minus 1. Right? In this case, the first occurrence is mid minus 1. Otherwise, the first occurrence is mid itself. Right? All right. So what I can do is over here is I can do mid minus minus. Mid minus minus. And then over here, my mid contains the index of the first occurrence. Now I can check. Now I can check if mid is even or odd. So if mid is even, mod 2 equals to 0, then I have to move towards my right. Yes, I have to move towards my right. How do I move towards the right? I say low equals to mid plus 1. Right? Otherwise, else I move towards the left. I say low equals to, high equals to mid minus 1. I simply say high equals to mid minus 1. Right? Perfect. But that does not really tell me when to stop. Right? That does not really tell me when to stop. So I have to make some other checks as well. Also, there is one more problem over here. That what if this mid turned out to be 0? What if this mid turned out to be 0? Then this A of mid minus 1 will give me an index error. Right? I will be trying to index at a negative value. That is not good. Right? So I have to take care of these things. So first of all, what I can do very quickly over here is I can first confirm this. Right? I can first fix this thing. I can say if mid is greater than 0, right? And A of mid minus 1 is equal to A of mid, right? Then do mid minus minus. Then do mid minus minus. So after this point over here at this line, mid will be the first occurrence of A of mid. Right? Mid will be the first occurrence of A of mid. Now if mid is even, we do low plus, we increment the low, else we increment the high. But once again, when do we stop? Once again, when do we stop? So we can check over here. If A of mid plus 1, right? If A of mid plus 1 is actually equal to A of mid, is not equal to A of mid, my bad. So we have the first occurrence of this element, right? We have the first occurrence of this element. And if the next element is not the same, then we have found the correct location, right? Then we have found the correct location. So what I can do over here is let me just erase this and write it properly. And also we will have to make sure that we check the boundary condition, right? So we will check if mid is less than n minus 1 and A of mid plus 1 is not equal to A of mid, then what do we have? We can just return. We can just return the mid because this is the correct answer. Is that clear? Yes, is the approach clear? So the approach is very simple. The approach is just saying that once you have these elements, all the elements come in pairs, right? All the elements come in pairs. So 0, 1 will come in one pair, then 2, 3, this will be the second pair, then 4, 5, this will be the second pair, until and unless this singlet element comes. Right? This singlet element comes. After that, we will once again have the numbers in pairs. We will once again have the numbers in pairs. So 7, 8 will be there, then 9, 10 will be there, then 11, 12 will be there, 11, 12 will be there, right? Now notice that before this singlet element, every new element occurred at an even index. Right? Every new element occurred at an even index. But after this, every new element occurs at an odd index. Right? So that is just what we are exploiting. All right? Cool. So what will be the time complexity of this approach? What will be the time complexity of this approach? So Abhay says, what if A of mid minus 1 equals to A of mid, then what are we doing with this? Right? So basically what I'm saying is, suppose we landed at this element. Right? Suppose we landed at this element was 7. Right? This and its previous element was 7. So if this is mid, then we are checking if a of mid minus 1, right, mid minus 1, if that is also the same as 7, if that is also the same as the same element, then move mid to the left, right, then do mid minus minus. Right, that will make sure that we are always looking at the first occurrence of an element. Right? Cool. So the complexity of this is just order of log n. Right? Why? Because this is a binary search, and at every time we are splitting the array into half. We are reducing the search space by half. Right? Is that clear? Cool. So this was a fairly easy question. Let us move on to a little slightly more difficult question. Okay. But before that, let me just give you a brief thing. So when you are finding a number in an array, right? You usually return some index, right? You usually return some index. Now, what occurrence is this? Which occurrence is this? Which occurrence is this? Basically, what I'm saying is, suppose that I have a sorted array 0, 1, 2, 2, 2, 2, 2, 3, 4, 5, 6. Right? Suppose that I have this sorted array. Right? So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now suppose I want to find the value 2. Right? I want to find the value 2 in this array. Right? So when I'm searching for the value 2, the value 2 occurs at more than one indices. Right? It occurs at all these different indices. So what index should my binary search really return? That is the question. Right? So yesterday we saw that, okay, we were returning an arbitrary index, right? As long as we found the index, it didn't really matter what occurrence we were looking for, right? So, I mean, that is perfectly fine. But usually what you will do is you will try to return either the lower bound. You will try to return either the lower bound, right? Which is basically the first occurrence, right? Or you will return the upper bound, right? Which is the last occurrence. Does that make sense? Yes. What if the array is not present? So lower bound is the first occurrence, right? Or if the element is not present, it is the location at which I can insert the element. I should insert the element. Insert the element to keep the array sorted. Yes. Similarly, the upper bound is the last occurrence. Right? Is that clear? Yes or no? All right. Cool. So basically, the question now is that if you have been given an array like this, and I ask you that given a value 2, you have to return both the first occurrence and the last occurrence of this element, then how will you do that? Right? How will you do that? So what if lower bound equals to upper bound? Well, that simply means that the element occurs only once. Right, Reshma? That simply means that the element occurs only once. So suppose that the question is that given this array and this value 2, you have to find both the first occurrence and the last occurrence of this array. So basically, if I give you 2, you have to return 2 and you have to return 6. So if the input is this array and 2, you have to return 2, 6. Right? So how will we do that? Yes, so this is very simple, right? This is very simple. We just have to make sure that we tweak a little bit of those -1s and +1s. Right? We just have to make sure that we tweak a little bit on those -1s and +1s. Right? So usually what we do is we write the loop like this. So while low is less than equal to high, right? And then what do? We say if array of mid, so we have mid calculation over here, we have something over here. We say if array of mid is less than key, right? If array of mid is less than key, then what do? We do lower bound. We do low equals to mid +1. We do low equals to mid +1, right? Otherwise, else if a of mid is greater than key, then we do high equals to mid -1. Right? Otherwise, If it is exactly equal, in the last class we saw that we can just return the mid. Right? We can just return the mid because we have found the location. But now we can't just return the mid. Right? Now, if we are looking for the first occurrence, suppose, if we are looking for the first occurrence, can we return the mid arbitrarily? No. Because what could happen is, when we calculated the mid, suppose we landed at this particular location. Right? We found the two, but we cannot return it, but because this is not the first occurrence. Right? This is not the first occurrence. So how do I ensure that this is the first occurrence? I will have to check over here. That first of all, else if mid should either be 0, right? If the mid is equal to 0, then it is my first occurrence, or a of mid minus 1 should not be equal to a of mid. Should not be equal to a of mid, right? Because if the previous element is equal to the same element, then this mid is not the first occurrence. Does that make sense? Yes or no? All right, that is fair enough. But then what does really happen then? If I write this code, there is a condition remaining, right? There is some condition remaining over here. Yes, there's some else condition remaining over here, right? So what do I really do in that else condition? Well, I have to absorb that else condition. It will have to absorb that else condition somehow. So basically what I need to do is, I need to make this thing less than or equal to key. Oh, sorry, I have to make this thing greater than or equal to key. Right? Basically, if I have found the element, but it is not the first occurrence, then I will still decrease my height. Right? Suppose I found the element over here, but it is not the first occurrence. The first occurrence occurs over here. Then what should I do? I should move left. I should decrease my height. Is that clear? But once again, the moment I do this, something else happens. Right? Another issue arises. What is that issue? That issue is that if I have this condition in my else if, I will never come into the else. Right? I will never come into the else. So what I will have to do is, I will have to move this particular condition on the top. Yes, do you guys agree? Do you guys see the problem? Because if I have less than here, and if I have greater than equal to here, then I will never go into that else condition, right? These conditions are exhaustive. Yes? So I will have to move this up. So what will my actual code look like now? What will the correct code look like now? For finding the first occurrence, what I have to do is, I have to check first of all, if mid is 0, right? If mid is 0, if a of mid equals to key, right? If I have found the value and either mid is 0 or a of mid minus 1 is not equal to a of mid, right? Only then, if I found the element and it is the first occurrence, only then can I return the mid. Right? Only then can I return the mid. Otherwise, so let me just put it over here. Right? Otherwise, if a of mid is less than the key, then I have to move up. Right? So I can say low equals to mid plus 1. Right? Otherwise, else, I can simply say high equals to mid minus 1. Right? And this is what my correct code looks like now. This is what my correct while loop looks like now. And this is for the first occurrence. Right? This is for the first occurrence. So this code is incorrect, this code is incorrect. Right? And this is the final correct code for the first occurrence. Can you similarly find the last occurrence? Can you similarly find the last occurrence? Yes or no? Yes, you just have to do it the other way around. Okay? You just have to do it the other way around. Basically, you have to make sure that a of mid equals to key and mid is equal to, either mid is equal to n minus 1 or a of mid plus 1 is not equal to a of mid. Right? That way we find the last occurrence. And when we are finding the last occurrence, this will be less than equal to, and this will not be, this will be less than equal to, right? This will come in less than equal to over here. So that is very simple. It is very simple to find the first and last occurrence of an element in an array. All right. Now suppose that I have an array which is sorted and has size n, has size n, and I tell you that given a value x, you have to count the number of occurrences of x in this array. Then what will we do? If we have to count the number of occurrences in this array, then what will we do? Yes? Jay says, instead of two binary searches, can we take a while loop both sides and find first and last occurrence? Yes, totally, Jay. We can totally do that. So let us we are going to explore that via this question. Right? We are going to explore that via this question. Suppose that we have this array. Right? Suppose that we have this array. This element is x, 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 and all the way till this location, it's x. Right? Then this is something else. This is y, y. This is a. Right? So if I am supposed to find the count of x's, right? This is a sorted array. If I'm supposed to find the count of x's, then I have two options. Either I can find the first occurrence, then write a while loop, then write a for loop, right? Till the last location of x. Yes or no? I can find the first occurrence and then I can increment the count one by one. I can go one by one and till I reach the last occurrence of s. And I can do a count plus plus. Right? I can do a count plus plus. If I do it this way, then what will be the time complexity? What will be the time complexity of this way? Well, to find the first occurrence, it will take me order of log n time. But after that, to count each of these values, I will have to count one by one again and again. Right? I will have to count one by one again and again. So it will take me order of n time for the counting. In the worst case, right? What if the entire array was full of the same values? Does that make sense? So in this case, this approach will be linear. On the other hand, can I do something better? Can I do something better? Let me just clear the banner. Just give me a second. Yes, can we do something better? Right? So what we can do is we can simply find the last occurrence. We can simply run a binary search to find the last occurrence. Right? This is one binary search. And we can also use another binary search, one more binary search, right, to find the first occurrence. Right? And then we can simply return last occurrence minus the first occurrence. Yes? Is that correct? Plus 1. Exactly. Right? Last occurrence minus first occurrence plus 1. All right? And that will basically give us the count of that element. Is that clear? Yes? All right, perfect. Cool. So I hope this is clear because this is very important. First of all, because whenever you do binary search, you have to understand that you're either going to be finding the last occurrence or the first occurrence. You're not going to be returning any arbitrary occurrence. Also, because in all of the further questions, whenever you are doing binary search, this is going to be very important for us. It is going to be very important for us. So let us look at another question. So suppose that we have been given two sorted arrays. Right? This is a very, very famous question. This question has been asked in all sorts of companies, right? Be it Google, be it Amazon, be it Facebook, be it DirectTime. All the companies have at some point asked these questions, this particular question, and this question is very, very, very frequent, right? And even if you try to search on YouTube, you will find hundreds of videos about this question. So this question is very important. The question is that you have been given two sorted arrays of length n and m respectively, right? So you have been given two sorted arrays. One is of length n, one might be of length m. Right? We don't really know which is larger, which is smaller, and both are sorted. Right? Both are sorted. The question is we have to find the median of both the arrays combined. Right? We have to find the overall median. Yes. Right. So first of all, let us look at what median is. Right? First of all, let us quickly look at what the median is. So suppose that I give you this particular thing. Suppose that I give you this array 1, 2, 2, 3, 5, 5, 6, 8, 10. Right? Suppose that this is my array, and let me put the indices as well. Right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. Right? So what is the median defined as? What really is the median? So median basically is another term for the middle element. Right? This is a loose definition. This is not the exact definition, but median, you can think of median as the middle element, right, of a particular collection. Now, what do we mean by middle element? If you're talking about a middle element, we should have some sort of order. We should have some sort of ordering, right? Yes. So that is why we are talking about a sorted array. So we are saying if we sort a particular array and then we look at the middle element, so in this case, do I have a middle element? In this case, do I have a middle element? How many elements do I have? I have 9 elements in total, right? I have 9 elements in total from 0 all the way till 8. So what will be my middle element? This will be my middle element. Yes, this will be my middle element. Okay. So basically, this is what a median is. Now, some of you might ask, all right, well, what if the number of elements is even? Right? What if the number of elements is even? So let us say that I add up 20 over here. Right? Now I have 10 elements. Now I have 10 elements, right? This is no longer 9, this is 10 elements now. Now there's no middle element, right? The middle element does not exist now. There are 2 middle elements. Both this and this are middle elements. Yes. Then what is the median? Well, in that case, median is the average of both of these. So in this case, this is both 5 and 5. So the median is just 5. On the other hand, let us try to change the values. So let us say this is 9, this is 9, and let us say this was 8. Right? If this was 8, then what will the median be? It will be 5 plus 8 by 2, right? Which is 13 by 2, which is 6.5. All right? Is that clear? Cool. So this is what the median is. Now the question says that you have 2 arrays. You have 2 arrays. Let us suppose 0, 0, 1, 3, 5, 8. Right? And you have another array. Let us suppose 4, 5, 6, 7, 8, 9, 20, 30. Right? Let us suppose that we have these 2 arrays. So let me put the indices very quickly. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7. Right? Now the question is not asking you to find the median of each of these arrays. That is not what is being asked. What is being asked is the median of the overall array, right? Of the overall collection. So basically, if I were to take all these elements, consider all these elements and sort them, right? Consider all these elements and sort them, then what will be the median? So what will be the median in this case? What will be the median in this case? If I write both the arrays in sorted form, I have 0, 0, 1, 3, 4, 5, 5, 6, 7, 8, 8, 9, 20, 30. Right? Yes or no? And this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right? That's an even number of elements. So the elements, what? The elements 6 and 7. So the median will over here be, the median will be 5.5. Is that clear? Yes or no? Is the question clear? We have been given 2 arrays and we have to find the overall median of the 2 arrays. Is the given array sorted? Yes. Both the arrays are individually sorted in ascending order. Right? Both the arrays are individually sorted in ascending order. Right? But I mean, relatively they are not sorted. So it is totally possible that this element is greater than this element. Right? That's totally fine. Okay. There's no relation between the 2 arrays. It is just that they are individually sorted. Yes. So yes, Shivani has a nice approach over here. Shivani says that let us very quickly merge the 2 arrays. So where did our comment go? Yes. So Shivani says over here that what we can do is we can merge the 2 arrays. So when you were doing the merge sort class, you read this merge algorithm, right? Merge algorithm. What did this merge algorithm do? Given 2 sorted arrays, it created a sorted array. Yes. And how much time did it take? How much time did this merge algorithm take? So if I have total of n plus m elements, if I have n plus m elements, then usually if I just do sorting, right? If I just do sorting in a naive way, then how much time will sorting take me? It will take me n plus m log of n plus m, right? This is how much time sorting will take me. However, if I use the merge algorithm, given that both the arrays are sorted, then I can do it in order of n plus m time. Yes, I can merge the arrays in order of n plus m time. Once I have merged both the arrays, then I can very quickly find the median. Yes, I can very quickly find the median. Right? Find the median. How much time will it take me? If I have merged both these arrays, how much time will it take me to find the median? So suppose that I have merged both the arrays. After that, how much time is it going to take me to find the median? So is it going to take us order of log n time? No, right? So finding a median is just order of 1. You just have to look at a of mid. Right? You just have to look at a of mid. If the number of elements is even, you just have to look at a of mid and a of mid plus 1. Right? So finding the median takes just order of 1 time, provided that I already have a sorted array. Right? So overall, if I do this merge thing, my overall complexity will be order of n plus m to merge the two arrays plus 1 to find the median. Right? To find the median, which is just order of n plus m. Is that clear? Order of n plus m. Well, that is fine. That is good. That is certainly better than the naive approach. Right? So this was the naive approach. So this is certainly better. But we can still do better. So this is not the best approach that we can use. So can we still optimize? Can we come up with an optimized approach now? Right? So let us quickly see what other approaches we have. So Ratnesh has a very, very nice question over here. Ratnesh says, can't we just use the median of medians? Median of medians, right? What does Ratnesh mean over here? Let us suppose that we consider these two arrays, right? Let us consider these two arrays separately. What is the median of the first element, or of the first array? So this is the first array. What is the median of the first array only? So this array has 6 elements. So the median will be what? So 0, 1, 2, 3, 4, 5, right? It has 6 elements. So the median will be at what index? No. So what Ratnesh is telling us is that let us try to find the median of medians. Right? Let us try to find the median of medians. So first of all, let us consider this particular array, A1. Right? This particular array has how many elements? It has 6 elements from this location to this location. So what will be the median of this particular array? It will be the sum of these two. It will be the average of these two, right? It will be 1 plus 3 by 2, which will just be 2. Right? Similarly, let us calculate the median of this array. Let us calculate the median of this array. Well, how many elements does this array have? This has 8 elements, right? And what is the median of this element or this array? That will be this 3 plus 4, right? This element at 3 and element at 4. So that is 7 plus 8 by 2, which is 7.5, right? Now, Ratnesh is saying, once we have these two medians, can't the final answer simply be the average? Can't the final answer simply be the average of these two? 2 plus 7.5 by 2? Well, no, that is not going to be always true. Right? That is not going to always be true. Is that clear, Ratnesh? Over here, we see that this does not really work. This is 9.5 by 2, which is 4.75. Right? And that is not the answer. The correct answer is 5.5 over here. So it doesn't really work. All right. So let me just remove Ratnesh's comment. So median of medians will not work over here. So we have to do something else. Yes. So what approach can we use? What approach can we use? So now we have to do some sort of a binary search. Right? We can use some sort of a binary search to optimize this solution. Right? So what we are going to basically do is we are going to binary search. There are multiple ways of doing this. Right? We are going to binary search on the index only of. We are going to binary search over the smaller array. Right? So first of all, suppose that this is A1. Suppose that this is A2. Right? So can I assume without loss of generality that A1 is smaller than A2? Can I assume that the length of A1 is smaller than length of A2? Yes. If that is not the case, then I can just swap those arrays, right? I can call this A1 and this A2 if that is not the case, right? So let us assume that A1 is the smaller array. So what we are going to do is we are going to binary search in this smaller array, all right? So we will have some low, we will have some high, and we will calculate a mid. All right. Now, once we have this mid, the question is, when will A1 of mid be the correct median, be the answer? What has to be true? What has to be true for A1 of mid to be the correct median? What has to be true? If A of mid is the correct median, then how many elements in A1, how many elements in A1 are less than mid, A of mid? How many elements in A1 are less than A1 of mid? When all these elements are less than A1 of mid? Yes or no? Do you agree? And how many elements are greater than this? Well, all these elements are greater than it. Yes. If A1 of mid is actually the median, right? Then what must be true? What must be true? Then half of the elements, right, across both the arrays, half of the elements must be less than it and half of the elements must be greater than it. Yes, half of the elements must be less than it and half of the elements must be greater than it. Cool. So let us check. Let us quickly check. So if A1 of mid is actually the median, then how many elements in A2 should be, or if this is the case, if this is actually the median, then how many elements in A2 should be less than A1 of mid? Right, that is the question. Right, so we know that in A1 there are mid minus 1 elements. Oh, there are mid elements, mid number of elements. So the count of elements in A1 that are less than mid is mid. Right? So the total number of elements that have to be less than A of mid. The total number of elements that has to be less than A of mid should be n plus m by 2. Yes or no? Should be n plus m or plus 1 by 2 actually. Do you guys agree? If I have this total sorted array, and this is actually the median, then half the elements will be less than it and half the elements must be greater than it. So if this many elements are less than it overall, right? And out of these, this many elements were already present in A1. This many elements were already present in A1. Then what is the number of elements that are present in A2 which are smaller than this A of mid? So this many elements were already present in A1. So this must be the number of elements. This must be the number of elements in A2. Number of elements in A2 that are less than mid. A of mid. Yes? Does that make sense? How can you say that length of A1 is equal to mid? No. We are not saying that the length of A1 equals to mid. We are not saying that. We are saying that assume that mid is the correct median. Assume that mid is the correct median. For that to be true, if there are these many elements that are less than it in A1, then how many elements should be less than it in A2? And this is the answer. This is the answer. These many elements should be less than mid in A2. So what we can actually do is, we can start with some low over here. We can start with some high over here, and we can calculate a mid. Now what we can do is, we can put a marker at n plus m plus 1 by 2 minus mid. Right? We can look at this particular index. Right? We will have 4 elements now. We will have 4 elements. We will have one over here, one over here, one element over here, one element over here. Right? So let us call these elements A, B, C, D. Let us call these elements A, B, C, D. A, B, C, D. Right? Now, when is this A of mid? When am I at the correct position? I am at the correct position when A is less than D and B and C is less than B. Right? If this is the case, then this marker, these two markers, they point to my median. Do they not? Yes. Do they not point to the median? Why do they point to the median? Because the number of elements over here and the number of elements over here is equal. Do you guys agree? The number of blue elements is equal to the number of green elements. Yes, and how are they equal? Because I have chosen to be. Right? Because I have used this formula to make sure that I land at the correct spot over here. Does that make sense? Cool. So, guys, if this is not clear to you at the moment, we will make sure to basically explain this with an example. So, just give me a second. My laptop battery is down. I will be back in a moment, guys. Let me just plug in my charger. All right. So, just. All right, we are back. Okay, so we will look at a concrete example, but let me first explain the idea. Right? Let me first explain. So basically, what we have to do is we have to binary search for a mid such that the property of the median, such that this property of the median becomes valid. All right. Now look at a concrete example. Let us look at a concrete example to further establish this. Right? Suppose that we have this array 0, 1, 1, 3, 5, 7. All right, and we have another array. Suppose 4, 5, 6, 8, 8, 12, 20, 30. All right. And let us mark the indices 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6, 7. All right. Now, which one is A1 and which one is A2? Which one is the smaller array? This is the smaller array and this is the larger array. Yes, this is the smaller array and this is the larger array. So let us have 2 pointers. Let us have the low pointer and let us have the high pointer. Yes, let us have the low pointer. Let us have the high pointer. Also, what is the value of n? The value of n over here is 6. And what is the value of m? The value of m is 8. Yes, there are 6 elements in the A1 array and there are 8 elements in the A2 array. Yes or no? Cool. So now we have this low and high. What will be the mid? What will be the mid? Mid will be 5 by 2, which will be 2. Yes, mid will be 5 by 2, which will be 2. So this is the midpoint. This is the midpoint. All right. And A1 of mid equals to what? It is 1. Right? Now the question is, how many elements in A1 are less than or equal to A1 of mid? How many elements in A1 are less than or equal to A1 of mid? Well, these many elements, right? This element and this element. Yes, there are 2 elements that are less than or equal to A1 of mid. What is the count of that? Well, the count is simply mid. Right? Mid is the count. Do you agree? Right. Now, if this one was actually the median, then how many elements in this array should be less than 1? Right? In this array, how many elements should be less than 1? Well, total there are 14 elements. Right? Total there are 14 elements. So if there is my median, then half of the elements must be less than it, half of the elements must be greater than it. Right? So basically what I'm saying is 7 elements should be less than or equal to it, 7 elements should be greater than or equal to it. Right? That is the property of my median. Right? Yes or no? Cool. So basically, if this is the case, and 2 of these 7 elements come from A1. Right? 2 of the lesser elements come from A1. Then how many lesser elements should come from A2? How many of the lesser elements should come from A2? Well, 2 are from A1, so 5 must be from A2. Right? 5 must be from A2. So all these elements should be less than 1. It should be less than this 1. If 1 was the median, then all these elements should be less than 1. Are they less than 1? Are they really less than 1? Yes or no? They are not less than 1, right? So 1 cannot be the median. Does that make sense? Because all these elements, they are not less than 1. So 1 cannot be the median. So my median is too small. In that case, I have to increase my loop. Right? I will try to find the median on the right hand side. Is that clear? Is that clear, guys? Yes. So basically what we are saying is that let us say that we are going to have a low and we are going to have a high, and we are going to calculate the mid as low plus high by 2, right? Now how many elements are less than mid, a of mid in the first array? Well, that is just mid. So how many elements should be less than it in the second array? How many elements should be less than it in the second array? That should be what? That should be n plus m plus 1 by 2 minus mid. Yes, that should be n plus m plus 1 by 2 minus mid, right? So what we can now do is, so this is the partition. This is basically the partition of A2, right? Now we can simply check. Now we have 4 elements. We have A1 of mid, we have A1 of mid plus 1, right? And we have A2 of partition, and we have A2 of partition plus 1, right? Is that clear? And we can check if this element is less than this element and this element is less than this element, then our partition is valid and we have the correct midpoint. Right? Then our partition is valid and we have the correct midpoint. All right. Why n plus m? Why this plus 1 thing? Well, this is just to make sure that the number of elements that are on the left are greater than or equal to the number of elements on the right. Right? That is just to make sure that the number of elements on the left are either equal to the number of elements on the right, or they are one more than the number of elements on the right. Okay. So if the number of elements is even, then there will be a mismatch, right? You can't have both the same number of elements on both left and right. So we will have one extra element on the left. Is that clear, guys? Just give me a second. My screen just went off. Interesting. Can you guys still see my screen? Yes, can you guys still see my screen? Guys, can you quickly tell me if you can still see my screen? I hope that you can. All right. So let us look at. Just give me a second. Let us look at some code for this. Okay? Let us look at some code for this. So what will really happen is, let us suppose that we have two arrays. So we have find median, and we have two arrays. We have A1 and we have A2. Right? Let us call this A and B. Let us call this the array A and the array B. All right, for simplicity. Now what we are going to do is, we are going to make sure that array A is smaller. We are going to make sure that array A is smaller. How can we make sure that array is smaller? How can we make sure that array A is smaller? Well, we can declare it over here, right? So we can say if the length of A dot length is greater than B dot length, right? If it is in fact larger, then simply swap the values of A and B. Right? So this will ensure that that this particular array is smaller. Right? And notice that this swap is just swapping the pointers. This is just swapping the pointers. This is not actually moving the arrays. This is just swapping the pointers. All right. So now that we have ensured that A is the smaller element, so now what we can do is, we can have a low and we can have a high. Right. So we can say that, all right, low, we can initialize low equals to 0, and we can initialize high equals to what? So what array are we searching over? We are searching over the smaller array. So we will say high equals to A dot length. Right? A dot length, right? And basically, let me also do one thing. Let me also save two values over here, n and m. So let me say, for simplicity, let me say that n equals to A dot length and m equals to B dot length. B dot length. Right? So we have saved the length or the length in nm. So now my low will be 0 and my high will simply be n. All right. Now I can loop. While my low is less than or equal to the high. Right. Now, what is the first thing that I should do? The first thing that I should do is I should calculate the mid. Right? I should calculate the mid. And what is the mid? The mid is simply low plus high minus low by 2. Right? Cool. Now, this mid is a marker in the first array. This mid is a marker in the first array. What will be my corresponding marker in the second array? As we just saw, that corresponding marker, that is called this partition, right? This is called this partition. This is going to be n plus m plus 1 by 2 minus mid, right? Is this clear to everyone? Is this clear to everyone? That this will be the partition? Cool. Now what we are going to do is, we are simply going to compare values. Right? We are simply going to compare values. We are going to say that if, okay, we are going to say if A of mid, right? If A of mid is less than or equal to B of partition plus 1, right? If A of mid is less than or equal to B of partition plus 1, and A of mid plus 1, or basically I can write it the other way. I can write B of partition is less than A of mid plus 1. Right? If this is the case, then what do we have? What do we have? We have two arrays. We have two arrays such that this element is smaller than this element, right? And this element is smaller than this element, right? So A is less than B and C is less than D, right? And we know that the number of elements over here is equal to the number of elements over here, right? If this is the case, then I have found my median. Right? So I have found my median over here. So I have found the correct midpoint, right? And I will actually return the median over here. So we will have two cases over there as well. We will look at that. But if that is not the case, then some other case will arise, right? Then some other case will arise. What case can arise? What case can arise? So either it can be that A is actually greater than B, right? It can be that A is greater than B, or it could be that C is greater than D. Yes or no? If A is in fact greater than B, let us suppose that I have something like 5 over here and 7 over here, right? And I have something like or let's say 12 over here, and sorry, not 12. Let us say 1 over here and 3 over here, right? So if this element is greater than this 3, then what does that mean? If this element happens to be greater than this 3, then what does that mean? It means that my midpoint is too high. This midpoint is too high, right? I have to move left. Is that clear? Similarly, if that's the opposite thing, right? If I have 5 and 7 over here, right? If I have, let's say, 12 and 15 over here, right? So if this element is greater than this element, right, then my mid should be on the right. Right? This value 7 over here, this is too low. So I should move to the right. Right? So that is what we are going to do over here. We are going to say else if A of mid is greater than B of partition plus 1, then I have to increase my mid. Right? So I have to decrease my mid. Right? So I will say high equals to mid minus 1. Right? Otherwise, I will say low equals to mid plus 1. All right. So this is the main while loop. Now there are some more conditions that arise. Those conditions are basically, let us take one more example. Let us suppose that we have this particular array and we have this particular array. Right? All right. Now we have two conditions. Either the combined length n plus m, either this is even, or n plus m, this is odd. Right? Either this is even or this is odd. If the length is odd, then what will be my median? If the length is odd, then what will be my median? This is A, B, C, D, right? We know the number of elements over here. So the number of blue elements is either equal to number of green elements, or it is equal to green elements plus 1. Right? It is either equal to it or one more time. Right? So if I found the correct midpoint over here, then what can I say about the median? What can I say about the median? The median has to be one of these two things. Right? The median has to be one of these two things. Yes or no? Yes or no, guys? And which one of these is the median going to be? Is it going to be A or C? Well, it is going to be the maximum of A comma C. Yes, the median over here is going to be the maximum of A comma C. On the other hand, if the number of elements are even, then what do I have? Well, in that case, what do I have? I have the max of, I want to find the maximum value on the left, right? I want to find the maximum value on the left. So max of A comma C, and I want to find the minimum value on the right, right? So a min of B comma D, and I want to take the average of those because the median will be average of two different values over here. Right? I want to take the average of those. Is that clear? Cool. So basically, what do I have to write over here? I have to check if n plus m mod 2, right? If n plus m mod 2 equals to 0, if it is even, then I have to return basically A of max. So basically, I have to return max of A of mid comma B of partition, right? The max of these two plus the minimum of A of mid plus 1 comma B of partition minus 1, right? And I have to take the average of these two. So I will add these two up and I will divide by 2. Right? That's a very long line, but I hope that it makes sense. Right? That is the case when my number of elements is even. On the other hand, if the number of elements is odd, then this is very simple. Right? Then this is very simple. I simply return. So I can simply return over here the max of A of mid and B of partition. All right. We can simply return the max of A of mid or B of partition. So this will basically be the code for finding the median of two arrays. Now there's one bug over here. Can someone catch that bug? This code is not entirely correct. There is one very, very crucial bug over here. And that bug is basically, let us suppose that I was searching in this array and I was searching in this array. Right? Suppose that while searching this array, either my midpoint became n minus 1, or if my midpoint became 0, right, then what do I compare? I don't have anything to compare, right? If my midpoint is this thing, n minus 1, then I can't compare A of mid plus 1 with anything, right? I can't really compare A of mid plus 1 with anything. Yes or no? So for that, to handle that, we can virtually append infinity and minus infinity to the left and right of both the arrays. All right. Yes, exactly. So Jay, even in that case, if the first array is only of size 1, so we will very quickly exhaust the mid. So to handle that situation, to handle that boundary case, we need to add infinity and minus infinity on the right and left side of both the arrays. All right. You don't have to actually append it. You can treat it virtually. Right? You can treat it virtually. Is that clear? Yes, आज कुछ ज़्यादा हो गया. Well, I mean, I would recommend that you actually try and code this up. When you try and code this up, this will, so I understand that you won't be able to, you will have to get practice on this. You will have to actually try and code this up to properly understand this. Right? But I hope that the intuition was clear. The code might not be clear to you, but I hope that the intuition was clear. Right? Cool. So now what will be the time complexity of this overall algorithm? What will be the time complexity of this overall algorithm? Yes. So we are doing a binary search, right? We are doing a binary search over what? We are doing a binary search over the smaller array. Right? We are doing a binary search over the smaller array. So what will be the time complexity? It will be order of min. So it will be order of log of min of n comma n. All right. It will be order of log of min of n comma n. Is that clear? Yes, Himadari, there are a lot of edge cases over here. So we always have to take care of the edge cases. I mean, the solution is very elegant, but the code only becomes difficult because of all the edge cases that you have to handle. All right. Tushar says, how are the corner cases rectified? The corner cases can be rectified by just adding a minus infinity to the left of both the arrays and a plus infinity to the right of both the arrays. All right. Basically, you can say that you have 4 values over here, right? You have 4 values over here. You have A, B, and you have C, D. You have these 4 values over here. Well, what if this midpoint was equal to n minus 1? In that case, if that is the case, then there is no A of mid plus 1, right? There is no A of mid plus 1. So what value should you consider instead of B? There is no B. B does not exist, right? So what value should you consider instead of B? You should consider infinity. Similarly, this value over here, if this is partition and this is partition plus 1, right? If there is no D element over here, then you should consider infinity in its place. Similarly, on the left hand side, if mid is 0, then on the left hand side you should consider minus infinity, and same for partition. Is that clear? So once you actually try to code this, things will start making sense. I don't want to give you the exact code right now, because then it will defeat the purpose of us trying to solve these questions. All right, you actually have to code this yourself, struggle a little with the edge cases, and once you figure this out, things will become clear. All right, cool. So let us move on then to the next question. Right. So the question goes something like this. That we have an unsorted array. Right, of size n. All right, and this array only has positive integers. Right, we have an unsorted array of size n, and this array only has positive integers. Now we have been given a value. X. Right, and we have to find the largest value of k. The largest value of k such that no subarray of length k has sum greater than or equal to x, or let us say just sum greater than x. All right. So that's a mouthful. Basically, what we are saying is, suppose that we have some array with some elements. Right? And we have been given a number x equals to 10. Right? Let me also give this array. So this is a 1, 5, 6, 2, 0, 1, 3, 5. All right, let us say this is my array, and I have been given some x equals to, let us make this a little smaller, perhaps x equals to 6. Right? Now we have to find the largest window size. Right? K is the window size. We have to find the largest window size such that in that window there is no window that sums up to greater than 6. Right? There is no window that sums up to greater than 6. So in this case, what will be the answer? Is the question clear? So if I make a window of size 1, this or this or this or this or this or this, then is the sum ever going to be greater than 6? Is the sum ever going to be greater than 6 if I have a window of size 1? No, right? So window of size 1 is valid. Right? Window of size 1 is valid. Size 1 is valid. Right? On the other hand, if I have windows of size 2, let us say this window, right? What is the sum of this window? The sum of this window is 6. Right? So 6 is okay. What is the sum of the next window? 5 plus 6. The sum of this is 11. Well, 11 is greater than 6. Right? 11 is greater than 6. So this window is not okay. And because this window is not okay, the window of size 2 is not valid. Right? Windows of size 2 are not valid. Is that clear? Okay. So we know that a window of size 2 will give me a sum greater than 6. So should I try a window of size 3 or above? Should I try a window of size 3, size 4, size 5? Yes or no? I should not try them, right? There is no point in trying them. Does everyone agree? Yes, because we have to find the largest window such that the sum of any sub-array of that size must be less than or equal to this summation value over here. Right? Let us take another example, perhaps. Let us take another example. So let us take one more array. So suppose this array is 1, 0, 3, 6, 4, 2, 7, 0. Right? And let us say that x equals to 13. Right? Let us say that x equals to 13. Okay. Now, what is the largest window? What is the largest value of k such that no window of size k has sum greater than 13? Right? So, does k equals to 1 work? Does k equals to 1 work? If I have windows of size 1, then is the sum going to be greater than 13? No, right? So, windows of size 1, they all have sum less than 13. Right? So, windows of size 1 are valid. Right? Every window of size 1 is valid. So size 1 is valid. This is valid. All right. What about windows of size 2? What about windows of size 2? Well, this has a sum of 1. This has a sum of 3. This has a sum of 9. This has a sum of 10. This is 6. This is 9. This is 7. Right? All the sums were less than or equal to 13. So windows of size 2 are also valid. All right. Let us try increasing the window size further. K equals to 3. All right. Now, what do my windows look like now? My windows are, so this is my window, first window, right? What is the sum of this? It is 4. Then this is the second window with sum 9. This is the third window, right? This has sum 13. This is the fourth window. This has sum 12. This is the fifth window. What is the sum of this fifth window? This is still 13. This is the last window. This has sum 9. Right? So still we see that window of size 3 is also valid. Is that clear? Window of size 3 is also valid. All right, let us try to increase it further. So let us try k equals to 4. All right, now what is the size of what is the sum of this? That is 10. What is the sum of this? That is 15. Right, the sum of this particular window is 15, and 15 is already greater than 13. 15 is already greater than 13. So windows of size 4 are not valid. Is that clear? And because windows of size 4 are not valid, windows of size 5, windows of size 6 will also not be valid. Right? All these will not be valid. Is that clear? Yes, is that clear? So if this is my array, if this is the input array, and this is the value of x that has been given to you, then what value of k should you return? What value of k should be returned? We should return k equals to 3. Right? We should return k equals to 3 because we have to return the largest size of window so that no window of that size has sum greater than x. Is the question now clear? Yes, is the question now clear? All right. So how can we approach this particular question? How can we approach this particular question? So guys, whenever you come across a new question, don't try to come up with the optimized approach right away. Right? Come up with the most brute force approach. Right? First, try to solve the question. Once you have solved the question, then you can try to optimize it. Right? Because some solution that works but is slow, some solution is always better than a fast solution that you never find. Right? So having some solution at least is better. Right? So let's think of a brute force approach first. Yes, so what can we do? All right. So let us look at two questions. Suppose I have a guess. Right? Suppose I have a guess for k. All right. Suppose I say that k equals to, let's say, 5. Right? Suppose I have this array and I have been given a value of x, let's say 20, and I am guessing that k equals to 5. Then how can I verify it? How can I check it? How can I check it? I have to consider every possible window of size 5. I have to consider every possible window of size 5. So how can I do that? How can I do that? I can either do two nested loops. So I can either say for I equals to 0 all the way till n minus uh, n minus n minus 5 minus 1, right? For j equals to 0 till 5 minus 1, right? And then I can say sum plus equals to a of j, a of I plus j, a of I plus j, right? And initially sum equals to 0, right? So doing this, what will this do? This will give me, so only, sorry, over here. I will have to say sum equals to 0 over here. Sum equals to 0 over here. So basically, after this inner loop, in each iteration of this inner loop, I will have I will have the sum of one window. Right? I will have the sum of one window again and again. So I will have to check if sum is greater than x, then return that window size is invalid, right? K is invalid. Right? After this entire thing is complete, I can say that K is valid. Right? So given a window size K, this is how I can check it. Yes or no? That seems like a very, very difficult approach to do, right? So can we simplify this a little bit? Can we simplify this a little bit? How can we do that? So are you guys aware of prefix sum? Are you guys aware of prefix sum? Suppose that this is my array. Suppose that this is my array and I want to find the sum from some start location to some end location. Right? If I want to do many queries of such form that find the sum of all these different elements, then how can I do that efficiently? I can calculate the prefix sum. The prefix sum of the array. Right? Let us say that this is the array A, then the prefix sum of array A will be P of A. Yes. Now, if I were to tell you to calculate A of I plus A of I plus 1 or plus A of I plus 2 plus all the way till A of j, then how can you express this in the form of prefix sum? How can you express this in the form of prefix sum? Well, this is simply equal to what? P of j minus P of I minus 1. Yes or no? Is that clear? Yes or no, guys? Alternatively, you can also rewrite this as P of j minus P of I plus A of I. Right? You can also rewrite this as this. They are the same thing. All right. So once I have this prefix sum, if I tell you that find me the size of window of size 5 starting from this location I. Right? If I ask you to find the sum of this window, then how can you do that? How can you do that? You can very simply do what? You can simply do prefix sum of I plus k minus prefix sum of I minus 1. Yes or no? This will give you the sum of this window, right? And to go over all possible windows, you can just write a loop for I equals to 0 all the way till n, right? N minus k basically. Yes. So that is the first thing that we can do to make our sliding window calculation a little simpler. Right? We can store the prefix sum. But the thing still comes that, all right, given a value of k, I can check if it is correct or not. But how do I find the value of k? How do I find the value of k? Currently, the approach that I have is start from k equals to 1 and try increasing it. Right? Try increasing it one by one. Right? If I do that, then what will be my time complexity? What will be my time complexity? I will have a loop for k. This will run for order of n time. Right? Then I will have a loop for checking k. This will also run order of n time. So my total time complexity will be order of n squared. Yes. Of course, I also have to consider the complexity of the prefix sum. But calculating the prefix sum is just order of n pre-computation. Right? Pre-computation. So this is actually order of n squared plus n, which is just order of n squared. Right? This is my naive, this is my brute force algorithm. All right? Can we improve this? Can we improve this? So Teju says that we can use binary search, right? But what should we binary search over? Teju, what should we really binary search over? Yes, so Prakash says that we can binary search for the value of k. So we are going to binary search for the value of k itself, right? So so what is the minimum possible value of k? What is the minimum possible value of k? What is that? What is the minimum possible value of k, guys? It is 0, right? It is 0. Basically, if some a of I itself is greater than x, then I can't have a window even of size 1, right? In that case, the value of k will be 0. On the other hand, what is the maximum possible value of k? Possible value of k, that is n, right? If I take the entire, if the sum of the entire array is still less than x, then that is the maximum possible value of k. So what I have to do is I have to binary search in this search space. So I can say low equals to 0, high equals to n, while low is less than equal to high, right? I will say mid equals to low plus high by 2, right? All right. Now, once I have the mid, what should I do? I should check window of size mid. All right. I should check window of size mid, and I will have another function over here. Check window, right? That takes a value of k and returns true or false. Right? This check window is going to do exactly this. So it is going to loop. It is going to say for I equals to 0 all the way till n minus k, right? If the prefix sum of I plus k minus prefix sum of I minus 1, right? If this is greater than x, if any of this sums is greater than x, then return false. Right? Otherwise, return true. Right? If all these windows are valid, then return true. Right? This is the check window functionality. Is that clear, guys? Cool. So we have a function for check window now. So what can we see over here? So if I check window of mid and this comes out to be true, if check window of mid comes out to be true, then what can I say? If a window of size k works, then can I return this? If a window of size k works, then can I return that window size as the final answer? Yes or no? No, I cannot. Because yes, this works, but this might not be the largest value that works. I have to find the largest value that works. Right? So if this is the case, then I have to increase my low. So I will say low equals to mid plus 1. Right? Mid plus 1. On the other hand, if this does not work, then I have to decrease my value of k. Right? So else, I will say high equals to mid minus 1. Right? High equals to mid minus 1. Well, when do we stop? So we can either stop when this loop exits, or we can explicitly check. That k works, but k plus 1 does not work. Right? If that is the case, then we can simply return. Is that clear? Even if you don't do that, that is fine, because this loop will automatically take care of it. Is that clear? So we will return when we find a position of k which works, but the immediate higher position, right? K works, but k plus 1 does not work. That will be our correct answer. Is that clear, guys? So after this while loop is over, I can simply return what? What can I return? So this will exit when low will become greater than high. Right? Low will become greater than high. How will it become greater than high? When I would just do low equals to mid plus 1. Okay, so I can just return low over here. Right? I can just return low over here, and that will be my size of the window. All right, cool. So what will be the overall time complexity of this algorithm? So let us take this step by step. How much time does check window take? How much time does one function call to check window take? This is simply a for loop. Right? This takes order of n time per call. Right? This takes order of n time per call. Well, what about this thing? This is login search, right? This is login search, but inside this login search, we are doing this order of n call every time. Right? Inside this login search, we are doing this order of n call every time. So basically, the time complexity will be order of n times log of n. Yes, order of n times log of n. Well, we also have to consider the prefix something. So this is for the prefix sum. This is for the binary search. Binary search. Oh, sorry. This is for the binary search. This login thing. Okay. This is for the binary search. And this is for check window. Check window. Right. So the overall time complexity is just order of n log n. Is that clear? Cool. Will you guys be able to code it? All right. So let us end the class at this point. We went quite over the timing today, actually, but that's okay, I guess. All right. So let us end the class at this. Please go to the link, find the assignments, and please try to solve it, because once you actually apply these, then you will learn much better. Right? Once you actually have to handle all the edge cases, once you spend a couple of hours on this, right, fiddling with the code or trying to debug it, trying to get all the test cases accepted, then you will learn much better. Okay. Cool. Perfect. Let us end the class then, and see you tomorrow then. All right, guys. Tomorrow same time, 6:30. All right. Bye bye. Have a good day.